right, great to be here. This module is on long-term thinking relative to interoperability and standards. My name's Wanda Reder, and I'm with GridX Partners. So in this topic, it's important to think about what the future has entail. And I'm going to be talking some about future-proofing. This is not really necessarily a standard or even a defined process, but more of an approach or concept where you're anticipating what might be needed in the future. And as you're doing that, thinking about the investments and that they will evolve over time. Now, our industry, as we all know, has been relatively static, and the technologies haven't changed a whole lot for maybe 100 years plus. But times are changing. We talked about make, move, used, and the changes have implications in technology all the way through that spectrum. So it's important to take that into account as we look at investments, because really those investments have to contemplate the evolution of what needs to be delivered in terms of functionality. And to the extent that we can think about the future, the lifespan of those will be longer, and we'll probably be able to get more out of them. You contrast that to the other side of the coin, where you probably have stranded assets that have to be replaced before they're fully depreciated. So, the result theoretically is that you have the latest technology, and ideally you wouldn't have to completely reinvest in new technology in order to enjoy that benefit. So some characteristics that will be sprinkled in, just kind of rules of thumb, is to pursue investments that are standards-based. It allows a mechanism that a lot of folks are behind it and that it can facilitate some interoperability. Choose solutions that are modular, scalable, flexible, so that what you buy today can take you through time in the future. Protocols can lead towards plug and play. We talked about USB, for example, and how easy that is today. It wasn't that way a few years ago. That's easier said than done. We'll learn some about that through the course of our discussion. That we anticipate future capability within the context of a broad plan. I think a lot of times we take a look at the here and now. And last is that remote operations and capability is considered in the decision making. We heard a bit about automated metering, and all of us have had to deal with this at some point in the last 10 years. I think well over 50% of the meters in the country are automated now. Probably more of them have two-way communications than one-way communication. But if you go through that series and think about the days of manual metering, we had multiple suppliers that provided meters. We had a workforce that was going from every meter to every meter once a month. And then we went into an automated state. Some of that paradigm of thinking moved into how fast we had to move the data, how often, the intervals of how that was read. And we got some incremental functionality. The workforce went away, of course. We probably don't have as many redundant suppliers in this equation anymore. We now have tamper detection. We can monitor voltage. We've certainly learned that the benefits from automated meter reading, especially with two-way, much surpass what we thought it would in the original business case. I think most will tell you that. But those that move forward with one-way in particular, now as needs are emerging with DER and such, perhaps if we would have asked the question with a longer horizon in mind, maybe those bets wouldn't have been made like they were. So the fundamental question is, if automated meter reading investments were future-proofed, would these emerging requirements be more readily available now at less cost? Shoulda, coulda, woulda question, I get it, but it's kind of pointing out the case that, as we're dealing with perhaps a need for dynamic time of use rates, unique rates if it's a prosumer or consumer for DER applications, smart inverter capability where there's grid forming functionality. We'll get into this, but maybe the role of that meter starts to change compared to what it was 10 years ago. So that's the idea of future-proofing. Let's take an example where I think they did a pretty good job. This is EPB Chattanooga, a municipality that's in Tennessee. They serve about 500,000 customers. And they went out to put in a distribution automation system, some people call that Flizzr, where the switches automate around a particular outage, and you're able to isolate that faster and get a lot of reliability improvement. The unique thing about this is that they ended up pursuing a fiber communication system that went throughout their 600 square mile service area that went past every single home. This is important because that fiber infrastructure provides communications that has functionality that will take them into the future for a whole lot of applications that go well beyond this distribution automation application. Another thing that happened is the switches that they selected not only provided capability for reliability, but they also have capability for future functionality. For example, they can see current and voltage in both directions. Settings can be changed. The protection schemes can be adjusted. They can pull out the radio and put in another one so that the hardware can remain on the pole, but to the extent that the communications or the software changes, there's mechanisms to do that. These are kind of hints of how the hardware, which is capital intensive, can remain on the pole, but you can see where the functionality over time can change. So let's walk through an example of how they realized reliability gains in the short term. And as I do this, I want you to notice two things. One is the amount of reliability gain, but the other one is the data and how the data is coming together to form a story. What they did is they coupled metering data with the switch data on a GIS platform so that you can physically see how things are being restored. So an outage that occurred in January of 2013, a tree fell in across the right-of-way and took out about 11,000 customers. This happened at 5:31 in the afternoon. So all of those red dots are customers that do not have power. So then, interestingly enough, the switches understood what was going on, and in about 28 seconds, 1,000 customers were restored. And then another 15 seconds, another 800 customers were restored. And then eventually they realized they could close in the last switch. An operator got involved, and they were able to actually get everybody up and running in about 6 minutes. So the interesting thing here is, if we would have done this the old-fashioned way, lock out, tag out, drive trucks around trying to figure out where the problems are and do manual switching, it probably would have taken 4 hours, maybe longer. So that, they can dispatch folks right to the problem, and they got a lot of reliability gains out of this system. So that actually, the investment was actually worth it just for this. But then if you think about what else is occurring here, migrating that data with GIS and switching and bringing that all together, they're now able to tell that story on TV, and customers get where the problem is, how fast they're able to restore, the benefit of the technology that's gone into the community. Tremendous advantage. And now, of course, they're using that same platform to incorporate more DER penetration, electric vehicles, and microgrids, because they were able to anticipate the functionality with the communication system and the two-way power flow. So I think this is a really good example of future-proof because it delivered the benefits early. It understood the functionality that had to be there from the get-go, but it also has the interoperability of data, switches, meters. Communication was designed for the future. The software can be changed remotely, and the list goes on. That hardware investment's there for the long haul, but the functionality evolves over time. Pretty neat. So taking that, I know that a lot of you are dealing with increasing DER penetration, especially from photovoltaics. This particular model came out of the Department of Energy, and I think it's particularly useful. It divides what functionality needs to occur within 3 different phases. And the first phase is really one where there isn't a lot of DER penetration yet, and backflow is not necessarily yet occurring. The next phase, phase 2, starts to see backflow, and we know that that's going to occur in some pockets, but not necessarily all. And then by stage 3, there's actually distributed energy markets. So maybe some people are selling to their neighbors, and the wires business ends up being used for a different purpose than what it is today. So, I think this is useful for a couple reasons. I just led a workshop using this, and it worked out pretty well, where you think about different streams of functionality that has to occur. And, in phase one, what do you need? You need to have, your processes in place for your interconnection agreements. You need to think about how DER is going to work into your system. You need to start thinking about the planning a little bit differently. You need to ideally have what types of inverters you're going to specify. Those kinds of things ideally are defined in stage one. By the time you get to stage two, you're starting to contemplate, where, reverse power flow is starting to cause problems. Planning's definitely a whole different game. That's moving into the operation arena. Your relay infrastructure needs to now think about the dynamic power flow, and on it goes. So, I think here it's a good example to say the functionality really evolves over time. What you snap a string in the beginning, where you don't necessarily have reverse power flow, is much different than as a lot of DER penetrates. And I often see a situation where certain states go, well, I'm just going to do what California did. I'm just going to do what New York did. We've all heard that. And the reality is California ended up getting out of the blocks before a lot of smart inverter capability was out there. So there's a whole lot of legacy infrastructure that can't necessarily evolve. So to the point that you can use phase one to define that and really leverage that infrastructure for the future, you're sitting in a way better situation than folks that got out into this early and can't necessarily migrate that capability. And I think that's, really a good example of how this model is quite useful. But it requires some thinking in the low penetration phases well before you're starting to see problems on the system. So this just defines, kind of the stage 1, 2, 3 in a little bit more detail. Stage 2, rule of thumb, more DER penetration, about 5% of peak load is where two-way power flow starts to occur. I mean, again, this is rough. You need some planning behind it. But then you're getting into situations where, you're going to have spots in the system where the relay protection, the operations for safety, all of that needs to be contemplated and working into the processes. And by stage 3, that's where markets and policy needs to evolve. In order to make this happen, interoperability and standards are key. So interconnectivity for the future. These bubbles, again, this chart came out of DOE, and it kind of says, okay, over the course of 5 stages, we start with kind of instrumentation, and then we get into interconnected, and then we get into intelligent types of capability. We've been on this journey in smart grid for a long time. And we're kind of in the stage 2, 3 mode, I would say, as a country. But I just take this and draw an analogy to a water heater really quick and think about, well, what do I want out of my water heater? I want to have hot water in the morning for when I shower and when I turn my spigot on, right? But think about that water heater in a little bit different way. What happens if that water heater can talk to my PV on my roof? All of a sudden, I can have a building that potentially is self-sufficient, but we need the two to talk together in order to make that happen. Let's take it a step further. How about if that water heater knows about constraints in the distribution system? Is there any reason that it can't kind of help out along the way if it could just understand and be able to control a little bit differently? As long as I have my hot water in the morning for my shower, right? And then there's the next one. Think about it from a bulk supply perspective. If a whole bunch of them understand the constraints in the transmission side, we can get a lot of impact to the extent that that capability was there. And I could overlay EVs and have the same conversation. So think about EVs and water heaters and solar all working together. Wow. That kind of breaks the paradigm of how we work today. And I just kind of plant that out there to get the juices flowing. I would say that adaptation depends on the willingness of regulators to approve funding for technology advances. A lot of times we make decisions on what we know today, what's happened in the past, and what other states have done. It requires understanding what technical advances are out there, and there's a reward mechanism for the value streams. I just mentioned a whole lot of value streams where we don't have mechanisms to reward it. And the last one is decisions should consider future capability and pathways and evolving benefits. I think this is a California example of what they're looking at for their clean energy electrification pathway through 2050. This actually is a snapshot of their by 2030 where they want to be. 80% decarbonization with renewables. Right now they're at about 40%. Electrification, 7 million vehicles. It means for the utilities, they'll have to put about 1 million of away from home chargers into the system. And then about a third of the buildings, using space and water heating from renewable sources. Anyway, all of this kind of maps to, what they're seeing where they need to be by 2040. I'm putting this out there because to the extent that you know that you need to do this by 12 years, you're going to design your system a lot differently. You're going to think about standards, think about roles, think about organization, think about information, do investments, do planning a lot differently if you know you have to hit this than if you're kind of working in what I know I need to do today. So it's really, really, really important to try and lay out this framework and get it clear and well understood. And I think this coordination diagram actually kind of helps to get our minds in that framework, thinking about the interconnectivity and the coordination that happens at the transmission system. I mean, obviously system operators need to have an understanding of what's going on with bulk generation, tying into IPPs, the independent power producers, understanding the changes of flow and transmission. Bulk storage is continuing to be more and more of, an element they need to consider. And then you move into the distribution system. There's more and more from a distribution operator that needs to occur because of the dynamic operations that are happening there from DER. So it might be an independent power producer that's on the, distribution system. Obviously the distribution system itself, constraints, storage that's on there, microgrids. And then you have the customer that's playing in a whole different way, whether they're using DER microgrids, maybe their usage patterns, demand side management. And then of course there's aggregators that we bring into the mix. So, we really need to think hard about how that distribution organization is going to see it, control it, manage it, because we're still holding the distribution folks responsible to be safe, reliable, affordable, resilient, efficient. So the decisions around how this is managed is really, really critical. They need to have the wherewithal in order to do that. I mean, if you think about it, the DER actually, if they're playing both at the distribution and the transmission, they're having to see constraints at both areas at the same time, simultaneously. You don't want to put one in front of the other. So the RMS of this is, what are the roles and coordination requirements? How can uncertainties of customers choosing their own technology alternatives impact the long term? Can the capability of the distribution utility be further leveraged as we think about other infrastructures, i.e. water, transportation, and the like? Where are the value drivers as we cut across those spectrums? So these are some of the things that I think really need to be considered as we map out this coordination state. A few takeaways then that I've left here on, just the importance of this end state being defined so that you can map the components into it and make the best decisions possible with methodology that's future-proofed and the use of standards that will hedge the bets for increased market alignment and interoperability provisions for the long term. Thank you.